This tweet looks like a bunch of nonsense, right? But if we open Pico 8, paste the code, and press run, it will start a simplified game of Agario, that browser game about eating circles. How is this possible? Pico 8 is a game development tool that allows you to make programs called cartridges, which you can share with others. Tweet carts are cartridges for Pico 8 which consist entirely of code which is 280 characters or less, meaning they fit in a tweet. These carts usually produce absolutely mind-blowing visual effects or interactive demos. There are no art assets or externally stored information. The only thing defining these programs is the code in the tweet. You can copy the code from the tweet, cold start Pico 8, paste the code, press run, and it just starts. When I saw the source code from these carts, I thought they had to be lying. To understand how this is possible, I wanted to try it myself, and with the simplest game I could think of. This is my recreation of Agario. Circles appear, move downwards on the screen, slower the larger they are. Larger circles eat smaller circles, and the game restarts when one circle fills the screen. It might not have most of the features of the actual game, like player input, but the essence of the rules are there, and the entire game comes from less than 280 characters of code. Here's how I did it. The programming language used inside Pico 8 is Lua. Lua is a simple scripting language. If you don't know much about Lua, it's pretty similar to other languages, so hopefully you can follow along. If you don't know anything about programming, I hope you'll also be able to follow along. Code doesn't usually look like this. I've just squished it to the smallest size it can be. Let me change it into something easier to understand. First, let's give the code some space. Every time you press space, or even enter, that counts as a character. To make the code fit in the tweet, I've squished everything together, but let's undo that. Some of these letters are just shortcuts for frequently used values. For example, if, in your code, you typed the number 128 3 times, you could instead make a shortcut t equals 128 once. Now, anytime we would have typed 128, we instead type t. T equals 128 adds 5 characters, but replacing each of the 3 128s with a t removes 6, saving 1 character. We apply this same principle to a few different values. I'll remove them to make the code more readable. Usually when writing code, you want to give each of your variables descriptive names. This is a table that will contain all of our circles, so instead of calling it p, we'll call it circs, short for circles. We'll do the same for each value. Now, we'll spread out this incredibly long line into multiple lines, and finally, add comments to explain each section. Now, the code is much easier to read, and we can break down how it was made. The first thing I needed to do was define how our game loop works. Typically in Pico 8, you use the callback function _update, which is called 30 times a second to update your game, and the _draw function to draw to the screen 30 times a second. To save on characters, we'll instead call a function called flip. When this function is reached, code execution stops for 1/30th of a second and the current frame is drawn to the screen. Then the code continues. Now, we can use a loop, which ends with the flip function to draw to the screen every frame. Instead of using something like while one, do, flip, we can instead save characters by creating a label surrounded in 2 colons on either side, and at the end of our code, writing go to the label name. This ends up saving about 1 or 2 characters over a while loop. Our program will start running code at the top, then, after it reaches the go to, it will be sent back to the label. So the things that should only happen when the game first starts go above the label, and everything else goes after. The first thing we need to do before the loop starts is declare an empty table called circs. Tables work like arrays or dictionaries in other languages. They can hold an arbitrary number of values or even other tables within themselves. You can add and remove elements from the table and iterate over every element of the table to apply the same instructions to each element. This is perfect for our game where we need an arbitrary number of circles to be created or deleted where each follows the same rules, differentiated only by their position and size. The first thing we need to do after the start of the loop is to clear the screen. In Pico 8, CLS clears the screen to whatever color you provide it. Color 7 is white. So far, our table does not have any circles in it. Here's the line of code that will add new circles to the table. The Pico 8 RND function returns a number between 0 and the input, with 1 as the default. So every frame, we generate a random decimal number between 0 and 1, and if the number is less than 0.1, we add a new circle. Elements are added to a table using the add function. The first element is the table to add to, and after that, we write the value to add to the table. The value we are adding is actually another table, which represents the individual circle and its various different components. Its x and y coordinate are set to a random number between 0 and 127, the resolution of Pico 8, and its size is set to a random number between 0 and 6, plus 1, to make sure that its radius is greater than 1. Next, we need to iterate over all the circles in the table using this loop. We can draw the circle to the screen using Pico 8's circ function. We provide the x and y coordinate, its radius, and a color. Color 8 is red. We add to the circle's x and y coordinate each frame, meaning the circles move down and to the right. They should move inversely proportional to their speed, meaning the larger they are, the slower they move. We can do this by taking some number divided by the radius of the circle. Also, each individual circle should check if its radius is greater than the size of the screen. If so, we call the run function, a built-in Pico 8 function that restarts the program. Next, we need to loop over every circle within the existing loop over every circle. This is so that each individual circle can check every other individual circle to see if they overlap. Before checking if they overlap, we check that the second circle this circle is looking at is not the same as itself. Circles should not try and collide with themselves. How do we tell if two circles are overlapping? There's no built-in function for this, so we need to do the math ourselves. Essentially, the question we are asking is this: is the distance between the center of each circle greater than the sum of their radii? The formula for calculating the distance between 2 points is the following. So, we can write an if statement that checks if the distance between the two circles' centers is greater than their combined radii, like so. But there's a common trick you can use to get better performance, and in this case, save some characters too. Getting the square root of a number and squaring a number are inverse operations. We don't care about the actual number that represents the distance of these 2 points. We just want to know whether or not that distance would be less than the combined radii of the circles. We can use this knowledge to remove the square root operation from the left side of the equivalency check, and instead raise the right side of the check to the power of 2. Since we are no longer getting the square root on the left, we are essentially comparing the distance between the circles squared by the combined length of their radii squared, which is equivalent to comparing the distance to the combined radii. This is good for performance, since the square root function is much more computationally expensive than the squaring operation, but it also saves us. If a collision is detected, we check whether the first circle is larger than the second. If so, we increase the radius of the first circle by the radius of the second, and use the del function to delete the second circle from the list of the circles, and vice versa if the second circle was larger. This completes the code for our Agario demake. The next step is to make it as small as possible by shrinking every variable to 1 character in length, adding back in the shortcuts, and removing whitespace to squish everything together. Now, I hope you have a clearer picture of how this jumble of letters and symbols is really just some very sensible and standard code, compressed to a minuscule size. We create a shortcut for the number 128, make a table to store the circles, make a shortcut for the random function, create a loop point at the start of each loop, first clear the screen, then iterate over each circle. For each circle, we create a shortcut for its radius, then a shortcut for its speed. Then draw the circle to the screen, and check if the circle's radius is larger than 128, and restart if so. We move the circle by its speed. Iterate over every other circle. If this circle is different from the primary circle, we check if these circles are colliding. If so, we check which is larger, growing the larger circle and deleting the smaller one. If a random value between 0 and 1 is less than 0.1, then a new circle is spawned with a random position and radius. Finally, we draw the frame to the screen and return to the loop. If you want to try Agario in one tweet, Open Pico 8 and copy the source code from the description of this video. If you want to learn more about advanced tweak carts, I've linked to a series of blogs by PixieNop breaking down some incredible code. If you want to see more videos about game development, subscribe to my channel. Thanks for watching.